Yeah.
Hello, everyone. Welcome to the post-lunch session of an online QIP short-term course on diagnostic of high voltage insulation organized by IIT Kanpur, Department of Electrical and Engineering. In this session, we'll have a talk by Dr. C.C. Reddy, sir, on damage equalization method for life estimation of insulation. Dr. Reddy did his Bachelor's of Engineering in Electrical Engineering from Government University College of Engineering, Hyderabad, India in 1995. After his BE, he worked as a lecturer and assistant professor in Electrical Engineering Department under J&T University, Hyderabad, India. After his ME and PhD from IISc, he joined J Power Systems Corporation, Hitachi, Japan, a joint venture company of Hitachi Cables Limited and Sumitomo Electric Company, and served as a senior R&D engineer in its ultra-high voltage research lab till 2011. Currently, he is working as an associate professor at Indian Institute of Technology, Ropur, since 2011 and is associate dean of student affairs. He is an associate editor of IEEE Transaction of Dielectrics and Electrical Insulation. Dr. Red had participated in academic industry collaborative research in Japan with several universities of Japan. He had also participated in the deliberations of Technical Standards Committee on Space Charge Measurements in Dielectric Materials. He is working on several projects with private industry like Reliance, Adani, KE Industries, etc., apart from public industries such as WDCPRI, etc. He has been organizing chair of IEEE CATCON 2017, general chair of IEEE ICIIS 2018 and 2020, general co-chair of IEEE ICIIS 2017-2019, and TPC chair of CATCON 2020, and international advisory member of ISEIM since 2011, held in Japan. His research interests are electric power cables technology, mechanism of conduction and breakdown in dielectrics, phase charge in dielectrics, nanocomposites dielectrics, power electronics, signal processing in HV engineering. We welcome you, sir. You can please proceed with your talk. Thank you.
Thank you for the introduction. I thank Professor Nandini Gupta and Alok for inviting me for this lecture. So I will share my screen now. I think I need some rights to be given, or what?
You should be able to. Because you're a panelist, you should be able to.
I'm pressing, but there is no message. It's not happening.
Then I'll just make you co-host also, which should solve the problem if there is one. Try now.
Even then. After, yeah, just 1 minute. Your camera, hello. Hello. Yes, now it has. Yes.
Okay.
Can you see my screen?
We can.
Yes, sir, we can.
So this is a lecture on damage equalization method for life estimation. As we all know that nanodielectrics have improved performance. For example, conduction is given here. With MgO nano filler, of 50 nanometers diameter. So around 100 times improvement is observed in the conductivity. Also, as per the breakdown, around 10 times improvement observed in the breakdown. Of course, the relation, 100 times in conductivity, 10 times in breakdown is as per the thermal breakdown mechanism actually. In DC, of course, the mechanism of breakdown is believed to be thermal in nature. So this is actually, both of them are initial performances, means when we are developing a nano material. So initial performance, it's not long-term performance. So initially means when we develop the nano composite on that day, on maybe during that time, the performance has shown, in conduction also there was improvement. Breakdown also there was improvement. Apart from these, several characteristics actually, many other properties improved with the nanofiller. Pre-inception voltage, impulse breakdown strength, partial discharge inception. But all these performances or properties or improvement in properties are initial. Initial means not after aging. So how it ages is very, very important, because if it ages faster, for example, this is the initial performance. So at time t is equal to 0, nano dielectric is having higher breakdown voltage. This is VT characteristics, lifetime characteristics. And this is virgin dielectric. So this is operating level, operating voltage, operating stress, you can say. So if the life is more with virgin dielectric than nano dielectric, then it's of no use having higher breakdown strength in the initial. The reason could be, there may be improved performance in the beginning, but due to compatibility issue over a period of time, due to, for example, even differences in physical properties such as thermal expansion, etc. So over a period of time, if the nano dielectric behaves badly and it ages faster than the virgin dielectrics, virgin dielectric material, means that which the base material which we use, then it is of no use. So it does not mean that initial performance is good, means long-term performance need not be good. So of course it may be good, but it need not be good. Such kind of question arises when we develop nano dielectrics, or when we develop any new materials. So traditionally a particle is seen as a defect. That consideration is there. Even now some people do believe that using a foreign material in dielectric material, always there may be a problem of this defect kind of situation. So although better initial performance is reported, there is no guarantee for a longer lifetime. So this is the background. So it essentially means that we have to test the material for its performance over a period of time, long time. So this is the traditional, voltage life or VT characteristics. In actually, we have taken it from mechanical people. For them, it is SN characteristics. Here, the fatigue life NF at stress S is given by SN curve equation. This is NF into S to the power of M equals to A. So the A is known as a strength constant. This is strength constant, it is called in mechanical engineering. Similarly, we have in electric V characteristic L, so exactly similar. So both represent a straight line on log scale. So this all engineers working in high voltage or dielectrics are expected to know already. So therefore, here this is the operating stress actually. At operating stress, we expect a longer life, minimum 20 to 30 years. So this is initial stress at which the breakdown strength is normally high, and this is the curve indicating LV to the power of n equal to K or NF into S to the power of M equals to A. So conventionally, how to find out this curve experimentally? So conventionally, we have long-term long aging experiments. So in that traditionally we have to apply particular voltage level V1, and it should not be so high also. What happens if it is high? The initial in the initial period, the slope need not actually reflect to actual aging at operating stress level. Therefore, normally we have to decide a stress which is lesser than the initial breakdown voltage. But here, at particular voltage V1, it's very difficult actually to decide which level we have to conduct this test. So if the stress is very low, this is actually logarithmic scale. The times will be very huge actually. Some of the samples may not break also. It's my experience also shows that this is very critical to decide at which field we will conduct this constant voltage test. So here the voltage V, a particular voltage V1, constant voltage is applied, and then test is continued for several samples. Say simultaneously also we can conduct. But there are issues when we conduct simultaneously, because breakdown in one sample may initiate due to that over voltage during that breakdown. If we connect all the samples together to a high voltage source, then due to local over voltage, the energy due to transfer of the energy, so there will be high voltage induced on the adjacent sample that may break early. So this kind of problems will arise. Of course, proper care has to be taken by connecting them through adequate impedance. So even then, what will happen? The breakdown at a particular constant voltage, if you are conducting on 10 samples, say, so all 10 samples will not break at a same point of time, and there will be a scatter. For example, some sample, these 10 samples might have broken like this. Now, for these also we have viable statistics, and then times to failure. This times to failure at this particular voltage, we use a viable graph, and then find out corresponding 63% value of the time at which which is the time to breakdown at this particular voltage. Say that is a point corresponding to this. Say similarly, we conduct the same test at a lower voltage, and again some 5-10 samples, so they break at a different instance of time, and then like this we will find out again the corresponding 63% of viable time to failure, and like this we have to do traditionally. But the problem here is the times to breakdown, as I told you, is distributed, and this is this fits for a viable distribution, means the largest time to failure is several times, several hundred times of the smallest value, and it may even tend to be several months or over a year also. So this kind of test is tedious, and say we have to truncate the experiment after some time, because we cannot continue with the experiment. Then an analysis known as censored data analysis, where same viable statistics will be used. We will assign some probabilities to the until the samples which failed, considering that samples which have not failed also. So that censored data analysis need to be incorporated for this. But there are associated inaccuracies in estimating the value of n. That is one thing. And then this is the tests may not conclude at a given a predicted time. So this is one of the biggest difficulty using this traditional, conventional, constant stress tests. Of course, the accelerated aging tests are also proposed. That's what I'm going to discuss now. So the data has a scatter. In this case, actually, conventional constant stress case, data has a scatter in times, as the failure times are stochastic in nature. And the largest time could be in years also. So can a material assessment wait for so long to decide? For example, we are developing a new nanomaterial. So for industrial application, so we need to prove that it really works in field. So therefore, when we are developing a nanomaterial or when we are developing a new material, say for example, we need quick analysis. So in a time bound fashion. So we have to decide whether that is good or bad in the long term, or how its performance will be. So especially manufacturers cannot wait for a long time, for long assessment time, unless if they're really implementing in that and the customer requires the long-term test, that is a different story. But normally for developing, we cannot wait for such a long time. So these accelerated aging tests are already, we know these things, that here the stress will be increased in a particular period of time, and then increase till the breakdown. So this is one advantage of this, because we can always, because we are increasing the stress, always at some stress definitely breakdown will occur. So these can be conducted in a time bound fashion. So these accelerated aging tests reduce the times of life estimation. So by increasing the stress in steps until breakdown. So the analysis is actually much involved. So as the aging depends on an unknown coefficient n. So here the LV to the power of n equals to k. So this n has to be estimated actually. So understanding was not adequate how to calculate the n value. Of course, probabilistic methods were there, very tedious methods were there, and very few reports are there for estimation of n using this accelerated aging test. So, but it is very important that such tests will reduce the time, and we can get the results in time bound fashion. So we can assess the materials, its aging, nature of aging, etc. So the main actually target is to estimate this coefficient n, so which decides the aging characteristic actually. So then how to do? So here conventionally damage is defined like this in mechanical engineering as per Miner's linear damage accumulation rule, or Palmgren-Miner's rule. The fatigue damage accumulation D is expressed as D equals to N naught divided by NF. This is actually N naught is number of cycles elapsed until that particular point of time. And NF is actually life under that stress, number of cycles under that stress, complete life. So this actually precisely represents a relative elapsed life actually. This is of course defined as damage, because the stress at which it occurs also not included in this. So, and each stress will have different number of cycles, NFI. For example, if I number of stresses are applied, then NFI is different for a different stress. So what D gives in this definition is relative elapsed life. So this disregards actually the strength in it. So, or in other words, it is per unit elapsed life with units as time actually. So this is what the traditional definition or conventional definition of damage represents in mechanical engineering. Now, similar can be defined in electrical engineering also. But what we did is a little bit different here. So damage is redefined here. It is reasonable to assume that damage is a function not only of time of application of a stress, but also on the magnitude of the stress. Because see, actually damage is proportional to N naught, the number of cycles it is stressed, and it what stress it is stressed, S to the power of m. So damage is defined like this: D equals to N naught S to the power of m by A. So where A is the strength constant. So what it is actually? It is actually, instead of elapsed life, this is per unit elapsed strength. Instead of per unit elapsed life, it is per unit elapsed strength. So even further simplification is possible, because A is a constant. We can ignore that for a given material. This is a constant, so we can ignore this dividing by this coefficient or this number. So damage now represent elapsed strength rather than elapsed life, of course. So alternately means if we ignore A, we can even define D as N naught S to the power of m. So the electrical counterpart, we defined it as DC is as D delta Ti into Vi to the power of n. Sigma is equal to 1 to R, because the sigma is used because we are using step stress test, right? Different voltages are there and correspondingly different times are there. So therefore the total damage is calculated as sigma I is equal to 1 to R delta Ti Vi to the power of n. So at the end of the life, what is end of life? End of life, so if you consider this, D is equal to 1 here in this definition. But in this definition, D is equal to A. A are the total strength. So the moment total strength is elapsed, then the sample is supposed to fail. So this is what is the definition of revised definition of the damage, as the material would have elapsed all its strength. So this is the definition we used in the work. And then damage also proposed as a random variable. So here traditionally, so we know that here, for example, LV to the power of n equals to constant. So if we do constant stress tests, the time to failure is actually is following L, time to failure, or life is following Weibull statistics. So it is again dealt with by Weibull statistics, right? Considering this as a random variable at a constant stress. Times to failure is considered as a random variable, and then time to failure is considered as a random variable, and then it is treated with Weibull statistics. Again, we already know breakdown strength tests we conduct. That is, initial breakdown test we conduct means time, very short time. So that also we will have different breakdown values at a given time. A given time means t is equal to 0 you may consider, because initial breakdown strength. Very fast rising ramp, or very fast step voltage we apply, and then find out the breakdown strength. More or less the times are in few hours or in minutes, say. So that's why these times are considered to be almost same. In that, again, we get the breakdown strengths at different V1, V2, V3 like this. Then these again we consider as in Weibull statistics, and find out corresponding 63%, 63.2% Weibull breakdown voltage. So this way we know that both L as well as V follow Weibull statistics. But we thought in a different way, why not complete L into V to the power of n will follow Weibull statistics? Yes, it should also follow, but this is defined as damage as in the previous case. So this is how D equals to n to the n naught S to the power of m. It is also important to note that all the samples are not registering same damage when they break. This is also important. Therefore, if we allow, so if we allow damage to be a random variable, then all the samples need not accumulate same equal damage, same amount of damage, same amount of damage when they fail. So this is how. But actually there will be some representative number. It doesn't mean that damage is not irrelevant. Yes, damage has relevance, but it is a statistical in nature. So this is what is very important to understand. All damages are not same. All samples will not accumulate same damage when they fail. But there is a statistical number which corresponds to particular sample that that is 63.2 percentage. Means, and the 63.2 percentage of samples will fail at a particular damage. So that is 63.2 percentage damage. So like that, we do have a number. So this is what is important. So here we treated damage as a random variable. So each sample would therefore break after accumulating its own damage based on its own voltage time history, and all such damages will follow a probabilistic or statistical distribution. This has been proposed in our paper actually. So of course, this various tests. Actually, our method, damage equalization method, does not require any step stress tests. It can be applied to any kind of test actually. But we propose it for step stress tests also here, keeping in mind that it is very quick in nature. We can find out we can assess the material in a very short time. That's very important. So here various tests and their significance is discussed in this slide. Accelerated life testing using constant stress is usually cumbersome, as the times to breakdown are normally very large. Consequently, accurate and usable data is difficult to obtain. So on the other hand, step stress techniques ensure faster availability of data owing to much reduced failure times. So here it is given here. So as I discussed earlier, since each curve has its own damage or its own life curve, here the statistical distribution is given interpreted like with different VT characteristics in this. So this is the VT characteristics of the samples, different samples. It is a spread. It's not a single line. That's what we recognize here. So these are life curves. So if we conduct a withstand stress or initial breakdown stress, it will be like this. So different samples would have broken at different voltage levels. You can see here. You can see here. See different samples. That's the intersecting points. Just to understand this kind of interpretation is given here. So different samples would have broken at different voltage levels, and we can find out a 63.2 percentage using Weibull statistics for this. Similarly, if we use constant stress test, so this line, this green line corresponds to constant stress test. Now the intersection of this green line with this life curves gives us the breakdown positions or times. For example, this is first sample, this is second sample, this is third sample. You can see the spread and you can see the times how far they are going. So if we decide go for constant stress test, of course I have drawn here, anywhere you can draw, the similar situation will be there, because this is further, this is logarithmic scale, you have to remember. So therefore, so this is the times to breakdown will be huge, and some samples we may not even test also. So we have to truncate there the experiments. This is a constant stress test, and then there is another type of stress, ramp test 1, ramp test 2, with different with different value of stress. Slope is used here. So this is again a step stress test 1, step stress test 2. So this is the actually characteristics given here. For constant stress test, log E equals to constant. And for ramp test, E equals to MT. So this is how we apply. M is the slope. Then log E equals to log M plus log T. So irrespective of whatever is M, our slope in VT characteristics on log scale is unity here. So they are all 45 degrees lines here. So this is what important observation here. E is equal to MT. M is the slope of ramp test, but it does not reflect in VT characteristic on log scale. So similarly, step stress tests also. So various tests are given here. For example, if I conduct a test using this step stress test 1 with particular value of step size, then I will end up in sample breakdowns at these levels because of the statistical distribution of damage or statistical distribution of VT characteristics themselves. So this is again depicted in the damage versus time characteristics here. So this is the spread of damage. So different samples will break at different damages. But this spread is constant, with the time also. Whatever time it is, the same accumulation of damage should happen. So, but the damage is not a single line. So this is, of course, a representative line is drawn here. Say 63.2% of damage that is drawn here. So if we conduct again the different stress tests are indicated on this. So how they will accumulate the damage and all. So the different kinds of damages, different levels of damages are shown here. So and then again the 63% damage will correspond to a representative value. So this is how. But the damages you see they are parallel straight lines, parallel to time axis because they should be independent. Whenever breakdown occurs, they should have accumulated same amount of damage. So that's how, irrespective of the nature of the test we do, the moment a sample acquires a particular damage, and if its damage is crossing, if its accumulated damage is crossing this, damage at which the breakdown occurs, so then the sample must fail. If you conduct step test using this test, it will fail here. Or ramp test like this, it will fail here, but same amount of damage would have accumulated. So on damage scale, if we see, so it should have attained same damage. So irrespective of time of failure, if it accumulates the same amount of damage, it must fail. So what is implied here is the moment they acquire same amount of damage means, for a particular sample, for this sample, say, so if it accumulates this damage in whatever test, whatever way we conduct, it will fail. So this what is, we need to equalize the damages. That's what is implied here. So each test procedure results in data points that are statistically scattered at the intersection of the following two characteristics. Inverse power law characteristic given by T into e to the power of n equals to D is equal to constant. These are life curves or constant damage lines for different values of damage. Life curves correspond to constant damage lines like this in the damage versus time figure. So the characteristics of test procedure are application of E with the time. This is another characteristic. So test procedure 1 and then life characteristics, or D is equal to constant characteristic. So these two curves, at the intersection of these, the samples will fail. So this is a depiction of statistical distribution of critical damage at breakdown. So I hope it is clear. And then of course this is about comparison of test times, and a simple mathematical analysis is done here. So if we use step stress characteristics like this, this green step stress characteristics, and then what is the time to failure? See, the time to conduct the experiment. This is the time taken to conduct the experiment. And then if we use constant stress test, this is the constant stress test characteristics. So it would have failed at this time instant. So the times to failure is related by this equation, this simple triangular triangle actually. If we calculate, we will end up with this kind of calculation. So amount of times in step stress test are far less than the constant stress test. So that's what this gives here. Of course, damage equalization method with step stress test combined, we need actually at least two types of tests are needed. For example, here, this is the damage characteristics, right? So to equate the damage, for example, at least two types of stress tests we have to conduct, or two types, any two types we have to conduct. Otherwise, we will not get a line like this. So, for example, we have conducted a step stress test here and another step stress test here, a ramp test or step test here, and then plotted a line for these two data sets. Then we will get a equalization, means the damage should be equal irrespective of the type of test. That's what is being proposed here. For example, we conducted step test 1 and step test 2. Then we found two different data sets of damages, and these two damages must be equal. So then that equalization gives us the characteristics actually of the damage. This is what is done in this in our proposal actually. Then why we cannot do with a single step test type is explained here. For example, you may do any number of samples, but if you used only a particular type of step test profile, for example, you have fixed 1 kV per minute. If this is your profile of application of the voltage, and you have conducted any number of samples, you cannot get a life characteristic because all of them will fall on this, say, for example, step stress test 1 on this line only. So if you fit the line, you will get such a characteristics. So it is therefore not possible to get estimation of n using step stress tests of only single type. This is very, very important observation. So initially, actually, it came with my practical problem. So when I was conducting that step test and trying to find out the VT characteristic, it was never possible because it is fitting on this kind of character line. This is what is happening in the background. So then, if you change, another step test means if you conduct different type of step test, same step size, change the step size, or change the time per step. So then it will be different characteristics. Then it will give us the data statistical distribution of data like this. And then this data set and this data set, if you equate means by fit a line, straight line, which has zero slope. That's it. Simple, very simple. Then you get the characteristic, the estimation of n. So that's what is proposed in this work. So here we propose at least two types of tests are needed. For example, this is one step size, this is another step size, or duration, step duration you change, step size you may keep 1 kV. Because this vertical step gives us the vertical resolution, means how much is the breakdown strength at what resolution, means what is the minimum resolution of your experiments. And this horizontal, this time step only delays the experiment. So what we did actually, we keep that 1 kV constant and then increase the step. Of course, irrespective of that, you will get, if there is any difference in the characteristics, definitely you will get damage. You can use damage equalization method and calculate the value of n. So equalization is very simple actually. It does not require very tedious statistical methods and all. Simple, fit a line for different step tests, then find out the value of n. So that's what is very, very simple. And the typical times of life estimation is 24 hours actually if you conduct the experiments continuously. So in extreme cases, it may end in a week or two. That's the advantage of using stress test in combination with damage equalization method. So this is the flow chart actually, in which so read the step durations of stresses. Of course, it is very generalized method is given here. Even E2, E3, and then sample till breakdown. These are only known values. Set the iteration number to j is equal to 1, and then value of index n, nj. Actually, n is iteratively found. The damage estimation has an equation, damage equation, delta t into v to the power of n. This n is unknown. So this n is obtained in such a way that the damages conducted, the damages of different tests will can be fit to a straight line. So at which the slope of this straight line is 0, means horizontal to the time axis, then that corresponding value of n is decided as the value of n for that sample. So this value of n is what is known as, it is known as endurance coefficient actually. It's very, very important for dielectric people or for high voltage people. So calculate damage first, we start from n is equal to 0 and calculate damages for each sample using the damage equation, whatever is given that initially, what the damage equation, the damage definition, and fit a straight line for all damages DC versus T data points using least square regression, nothing else, just very simple, and estimate the line slope. Go on estimating the line slope for different values of n, and whenever it becomes 0, just stop the iterations, and then that corresponding n value is the endurance coefficient. So this is very simple. Actually, the slope which is being calculated in this method is always following such kind of characteristics. Always. We have done for many samples and many different dielectric materials, but all of them are following. So it never becomes negative until it goes like this and then increases suddenly, and here there is a peak always, and then it becomes 0. So this value is our requirement actually. When the slope becomes 0, the damage is invariant with type of test. So that's where we have taken the value of n. So using that, after n is estimated, the critical damages are given here actually for various samples. This is for PVC at 70 degrees centigrade, and this is the data for PVC at 50 degrees centigrade. So here LDPE for 25 degrees centigrade. So these are the these are combined data of all types of tests conducted. All types of means different step sizes we have used and then conducted. This includes complete data. So it fits very well to Weibull statistics. This is damage actually. Damage on a Weibull scale, Weibull probability. So again, we have seen for this, slight, third parameter is also visible. So this is plotted in Weibull 3P here. This is Weibull 2P characteristics, and this is Weibull 3P. So here the third parameter is also visible. The third parameter is the significance is that this is the minimum damage at which the breakdown will occur. So until this damage accumulation, so no sample is expected to fail. So that's what is the significance of this minimum damage. So here you can see the fitting to the Weibull characteristics, very nice actually. And we have compared the results with literature using conventional methods actually. So here step stress tests are used, and the method damage equalization method is also applied to constant stress accelerated life testing also. So in this case, power law exponent by Hirose Professor Hirose, and here 1.97 was his estimated value, and DEM, it is damage equalization method, also 1.97. He has two types of data here, beta free and beta fixed. Here 1.6 is the beta fixed one, and then DEM is estimating as 1.71. And another professor from China, so it is 13.29 in his case, and the damage equalization method predicts it as 13.15. And several other samples also we have done. This was the result initially when we proposed this method. After that, we have been successfully using it for several samples, and practically expected values are being obtained. And another statistical features of this method is also being also submitted actually under review. The paper is under review. So the method actually successfully worked. Test results confirmed well with long-term test results using maximum likelihood method actually. So with the results of life assessment became a quick characterization technique for the assessment of the materials, especially when developing a new material. The test results are of utmost importance. So using step stress test, if we conduct a single step stress type of test, we can never estimate the endurance coefficient. But if we have minimum two different types of tests, if we conduct, then the data can be used to estimate N with very simple technique, that is linear least squares regression, by equating the damages of different tests. So this is what is the what we have done. So this is the end of my presentation. You may ask the questions, please.
Thank you, sir, for such an informative. We'll proceed with the question answer session. Participants, you can please write Q&A. We have a question from Balaji Sriram.
Okay.
You have been allowed to talk, Balaji. You can unmute yourself and ask the question.
Hello, sir. This is Balaji. In slide number 11, I have a question. There you had shown that samples with lower applied voltage undergo a faster breakdown. I couldn't understand that part. Can you please clarify?
Slide number 11.
Yes, sir.
Tell me.
Here, samples with lower applied voltage. Let's take the lowest red line curves or red slope. And then we are applying a voltage somewhere between 10 to the power 1 to 10 to the power 2, and it fails at it fails lower, no sir? That is the question. It intersects the green line at a lower time value than the others.
Yeah. So what is your question actually? So this
with lower applied voltage, it is intersecting the green line at a lower time instant. It should intersect
green line is the applied voltage. Balaji, green line is the applied voltage. That red line or that other color is the other color. Other color is actually lifetime characteristics. This is life curve. Green line is the applied voltage.
So where both of them intersects gives us the breakdown time, no sir?
Yes.
So that is the question. With lower applied voltage, the green line intersects the red line at a very lower time than the other curves.
See, all are life curves only. This particular sample will break early. The next sample will break at a later time. The next sample will break even a larger time, like that. So I told about this applied voltage. If you increase the applied voltage, of course, times will be shorter. I have taken this applied voltage as the at this position. So just to show you that if the voltage is low, then the times to failure will be large because other samples will go further and further. So if you increase the applied voltage, see, if I put applied voltage somewhere here, this sample would have, if you trace it back, this is logarithmic scale, of course, it during the application itself, this sample would have failed. The other samples also would have failed up to this time, say, if I draw another line like this. Okay, so that's what I mean. If you increase the stress level, then of course the times to failure will come down. But if you increase the applied, if you decrease the applied voltage, the times to failure will be very large. So that's what I mentioned, that I have used here just to indicate that it can become very large.
Okay, sir. Now it's clear. Thank you.
Okay.
Do we have any more questions from the participants? Okay, Asha ma'am has raised her hand.
Hello, sir. Good afternoon.
Good afternoon.
Sir, okay. Actually, maybe I have not understood completely. Like, how are you deciding the step size for the time? As you have mentioned that you have done about 3 tests and you have fixed the voltage like 1 kV. But you are increasing the time step size for the time. So how are you deciding that step size? I couldn't understand it completely.
Step time. See, it can be based on your convenience.
Okay, but according to the convenience, if I increase the step size, that maybe the breakdown of that sample may occur. So are you then you have to decrease that step size. So it will be a very repetitive procedure. So
what is your question is not clear to me.
okay. Here in this graph, you have said that you have fixed the voltage, step size for the voltage as 1 kV, and you are increasing the step size for this time.
Step time I am increasing. Yes, step time I am increasing. See, 1 kV per minute, 1 kV per hour, 1 kV per 2 hours, 1 kV per 3 hours, something like that we have done.
Okay, but during this maybe the breakdown of the sample may occur. Then again, you will do the same exercise.
During this, see, each time a sample will fail, obviously.
Yeah, okay.
Each time a sample will fail.
Okay. So
Definitely.
This is like I am doing every time I am doing it on a fresh sample. But
Yes.
Okay,
On a fresh sample. If you do on the same sample, of course, if you do on the same sample, you have to continue the step from wherever it has broken.
Yes.
Okay, that is very important. You have to continue because damage already accumulated, some damage is accumulated. You have to continue from wherever you have broken. So from there you have to continue. So
Exactly.
it will be difficult actually. So how to suddenly go to that voltage level and continue? That's why each time we have to apply the a fresh sample and one single sample at a time. That is what is done. Of course, it is not mandatory to do like that. If we have a software, so which can drive a DC source or AC source, suddenly if you can go to that level and then continue the experiment, that is well and good, not a problem.
Okay, sir. Thank you.
But even with each fresh sample also, so the amount of time consumed for this kind of test is limited and then predictable. So unlike constant stress test. Constant stress test, we are not sure when a sample fails. 10 samples are under test. It may continue for 1 month, 2 months. Sometime we have to stop that. And then data has to be truncated. The sensor data analysis has to be done. So such kind of problems are there with constant stress tests.
Okay, sir. Thank you.
I think there are no more questions from the participants. Thank you, sir. We'll close down the session for day 3. We'll meet again for day 4, starting with the time domain assessment of power cables. Thank you all.
Thank you, Professor Reddy.
Yeah, thank you,
for
everyone.
this
Professor
time
Reddy,
and,
for your beautiful talk. It was very illustrative and very interesting. Thank you very much.
Thank you, madam.